Think about the last glass of water you drank. When was it? An hour ago? This morning? If you are like most adults in the developed world, you are already mildly dehydrated right now as you watch this. Not severely, not dangerously, but measurably. Not severely, not dangerously, but measurably. Studies consistently show that between 75 and 80% of Americans are chronically mildly dehydrated. And the effects of that mild dehydration on cognitive performance, cardiovascular function, kidney health, and metabolic efficiency are documented, specific, and almost universally underestimated. But today I want to take you through something more extreme. Not mild dehydration, a complete cessation of water intake for 24 hours. Not because I am recommending it, but because walking through what your body does hour by hour when it is denied water is one of the most illuminating ways to understand how much of your daily biology depends on a molecule most people take entirely for granted. Water is not simply a beverage. It is the medium in which every chemical reaction in your body occurs. It is the transport system that carries nutrients to cells and waste away from them. It is the temperature regulation system that keeps your core body temperature within the narrow range compatible with life. It is the structural component of every cell membrane, every joint, every intervertebral disc, every vitreous humor in your eye. And when it is absent, the consequences begin not over days, but over hours, in a sequence that is documented with precision and that most people would find genuinely alarming if they understood it. Today, we are going through that sequence, hour by hour, because water is the most fundamental biological requirement of your body, and the science of what happens when it is absent is one of the most important pieces of physiology you will ever understand. Before we start the clock, you need to understand your body's relationship with water at baseline, because the urgency of the dehydration timeline only makes sense in the context of how precisely your body regulates its water content. Your body is approximately 60% water by weight in the average adult male, slightly less in females due to higher proportional body fat. This water is distributed across three main compartments: intracellular fluid, inside your cells, which holds approximately 2/3 of your total body water; extracellular fluid, outside your cells, including blood plasma and interstitial fluid, which holds the remaining third, and a small but critical portion within specific structures, including cerebrospinal fluid, synovial fluid, and the aqueous and vitreous humors of the eye. The regulation of this water distribution is controlled by two primary mechanisms. The first is osmolarity, the concentration of dissolved particles in your body fluids. When osmolarity rises, when you lose water without losing the dissolved solids, your hypothalamus detects this through specialized osmoreceptor neurons and triggers two simultaneous responses: the sensation of thirst and the release of antidiuretic hormone from the posterior pituitary, which signals the kidneys to conserve water by producing more concentrated urine. The second mechanism is volume sensing. Specialized baroreceptors in the heart and great vessels detect reductions in blood volume and signal the renin-angiotensin-aldosterone system to retain sodium and water in the kidneys, simultaneously triggering the sensation of thirst through a separate neural pathway. These iki sistemler olağanüstü derecede hassastır. The osmoreceptors in the hypothalamus can detect changes in plasma osmolarity of as little as 1 to 2%, a change that corresponds to losing less than half a liter of water without replacement. Your body knows it is losing water before you consciously register thirst, and it begins compensating before you notice anything is wrong. Hours 0 to 2. The clock begins with your last sip. In the first 2 hours, if you have been adequately hydrated and not exercising or sweating, very little changes at the physiological level. Your kidneys are producing urine at their normal rate, approximately 0.5 to 1 milliliter per minute, and the fluid lost is simply not being replaced. Within the first hour, the most sensitive osmoreceptors in the hypothalamus are already registering the earliest rise in plasma osmolarity. You may not feel thirsty yet. The conscious sensation of thirst lags behind physiological detection of osmolarity change. But antidiuretic hormone secretion is already rising, signaling the kidneys to produce more concentrated urine before you have any awareness that conservation is needed. This is one of the most important principles in hydration biology. By the time you feel thirsty, you are already physiologically dehydrated. Thirst is a late signal, not an early one. Athletes, military researchers, and occupational health scientists all use objective markers: urine color, specific gravity, body weight change, rather than thirst to assess dehydration status, because thirst consistently fails to detect mild dehydration accurately. Hours 2 to 4. By hours 2 to 4, the cumulative fluid deficit is beginning to produce measurable physiological effects in most adults under normal temperature conditions. Plasma osmolarity has risen by approximately 1 to 2%. The kidneys are producing noticeably more concentrated urine, the characteristic dark yellow color that reflects high urobilin concentration and reduced water volume. Blood viscosity is beginning to increase. As water moves from plasma to maintain osmolarity equilibrium, plasma volume decreases, and the concentration of red blood cells, proteins, and dissolved solids in the blood increases. The heart must now pump thicker blood, generating more internal friction with each beat and requiring greater cardiac effort to maintain the same cardiac output. A 2011 study in the Journal of Nutrition found that a fluid deficit of approximately 1.5% of body weight increased heart rate by an average of 3 beats per minute and produced measurable increases in perceived exertion during mild physical activity. A 2012 study in the Journal of Nutrition found that women with a mean dehydration level of 1.36%, less than a 1 kilogram fluid deficit in a 70 kilogram adult, showed significantly impaired concentration, increased perception of task difficulty, and elevated headache frequency compared to adequately hydrated controls performing the same tasks. A 2012 study in the Journal of Nutrition found that women with a mean dehydration level of 1.36%, less than a 1 kilogram fluid deficit in a 70 kilogram adult, showed significantly impaired concentration, increased perception of task difficulty, and elevated headache frequency compared to adequately hydrated controls. The brain is approximately 75% water. Even modest reductions in brain water content alter neuronal membrane potential, neurotransmitter concentration in synaptic clefts, and the mechanical properties of the brain tissue itself. Cognition is among the first functions to show measurable deterioration as dehydration develops. Hours 4 to 8. Between hours 4 and 8, the fluid deficit has typically reached 1.5 to 2.5% of body weight in a sedentary adult at normal temperature. The kidneys are at maximum water conservation. ADH is fully elevated, and collecting ducts are maximally permeable to water. Urine is dark amber. Urine-specific gravity is approaching 1.030, near the upper limit of what healthy kidneys can achieve. Physical performance is measurably impaired. A 2007 meta-analysis in the International Journal of Sport Nutrition and Exercise Metabolism, covering 34 studies, found that 2% body weight dehydration reduced aerobic exercise performance by 10 to 20%, driven by decreased blood volume, affecting oxygen delivery, and by plasma hyperosmolarity, directly impairing skeletal muscle contractile biochemistry. Driven by decreased blood volume affecting oxygen delivery, and by plasma hyperosmolarity, directly impairing skeletal muscle contractile biochemistry. The clinical pinch test used in emergency medicine becomes measurably abnormal around 5% dehydration, but visible changes in skin plumpness appear earlier, hours 8 to 16. By hour 8 to 16, the fluid deficit is approaching or exceeding 3 to 4% of body weight. The physiological consequences extend from performance impairment into clinical concern. Headache is nearly universal at this dehydration level. As the brain loses water content, slight reductions in brain volume cause the meninges and cerebral vasculature to stretch, activating meningeal pain receptors. A 2004 study in cephalalgia found that rehydration resolved dehydration-induced headache in over 90% of cases within 30 minutes, confirming the direct causal relationship. The cardiovascular system is under increasing strain. Blood pressure is declining as blood volume falls, and peripheral vasoconstriction reaches its limits. Heart rate is rising to maintain cardiac output against reduced stroke volume. The pre-shock state, where the body's emergency protocols are active and the margin for compensation is narrowing. The pre-shock state, where the body's emergency protocols are active and the margin for compensation is narrowing. The tubular cells of the kidney start dying from oxygen deprivation. This is the cellular mechanism of acute kidney injury from dehydration, and it is why hospitalized patients who cannot drink receive continuous intravenous fluids. By the final hours of a 24-hour water fast, the physiological state approaches what emergency medicine classifies as severe dehydration, moving toward hypovolemic shock. Total body water deficit is approaching 5 to 8% of body weight. The compensatory mechanisms active through earlier hours are failing. Blood pressure is significantly reduced. Heart rate is markedly elevated, a baroreceptor-driven tachycardia attempting to maintain cardiac output as stroke volume falls. Skin is pale, cool, and dry as peripheral vasoconstriction diverts blood from the skin to protect core organs. Confusion and altered mental status emerge as cerebral perfusion falls below the threshold required for normal neural function. Electrolyte disturbances are accumulating. Serum sodium has risen progressively as water is lost without the sodium normally accompanying it. This hypernatremia, high blood sodium, is directly toxic to neurons. Neurons in a high sodium environment lose water by osmosis, shrinking and altering their membrane potential. Severe hypernatremia produces seizures, coma, and in extreme cases brain hemorrhage from mechanical traction on cerebral vessels as the brain shrinks within the skull. A 2015 review in the New England Journal of Medicine confirmed that serum sodium levels achievable within 24 hours of complete water restriction in hot conditions are associated with neurological injury and mortality risk that increases steeply with severity and duration. Death from dehydration in adults typically occurs within 3 to 5 days under normal conditions and within hours in extreme heat. The 24-hour mark represents the transition from severe physiological strain to the beginning of organ failure. Here is what I want you to carry out of this video. The sequence we have just traced, from the first hour's subtle osmolarity rise to the 24th hour's cardiovascular and neurological crisis, is the extreme version of a continuum that you are somewhere on right now. Most people in the developed world sit at 1 to 2% dehydration as their chronic baseline. Experiencing the cognitive impairment, the cardiovascular strain, the kidney stress, and the headache susceptibility documented at those mild levels, without connecting those experiences to the amount of water they are or are not drinking. Experiencing the cognitive impairment, the cardiovascular strain, the kidney stress, and the headache susceptibility documented at those mild levels, without connecting those experiences to the amount of water they are or are not drinking. The brain needs water for the electrochemical environment in which neural signaling occurs. The joints need water in their synovial fluid for lubrication and load distribution. The intervertebral discs are 80% water at birth and progressively desiccate with age, a process that adequate hydration slows. Water is not a wellness trend. It is the medium in which your life occurs. The science of dehydration is not complicated. The implementation is even simpler. When did you last drink a full glass of water? Not coffee, not juice, water. Drop it in the comments. And subscribe to the channel because next week we are going deeper into the specific daily hydration habits the research shows most effectively protect long-term kidney, cardiovascular, and brain function. And I will see you there.